Hey guys, so today I'll be talking about how to find eigenvalues and eigenfunctions of second order differential equations, and as a sort of like extra part, I'll be also proving that the solutions to the functions are orthogonal. So first we have a second order differential equation y prime prime plus lambda y is equal to 0, and then we have these bounds within our datas, and we also have the boundary conditions given here. Essentially, when it means to find eigenvalues, it means to find eigen lambdas such that this equation holds true, and then the corresponding y's for these lambdas such that this equation holds. So first what we do is we recognize that as a second order differential equation should have a form like this, and we plug in our boundary conditions. So from our boundary conditions, we get these two equations, we move them to the other sides, and we get a set of equations like this. Realize that this is sort of like an x and y, and whenever we solve two equations that are the form like this, we would set the determinant to equal to 0. So we take this term times this term minus this term times this term, we get this. Simplify to get this equation, and then we eventually find that square root of lambda is equal to n, where n is a non-negative positive integer. So whenever specifically n is equal to 0, we have cosine of 0 is equal to 1, and when n is greater than 0, we have sine n theta and cosine n theta. Now we're going to prove that these two eigenfunctions are independent. So for this part, essentially you want to demonstrate that any combination of eigenfunctions that you have will result in 0 whenever you integrate from the boundary condition 0 to 2 pi, as long as n and m are not equal. So using some special trigonometric functions, we get cosine n theta times cosine m theta is equal to this, which is equal to 0 if n does not equal to m. And similarly for sine times sine, we have the same solution, and sine times cosine, and we also have this equal to 0. So thus we've shown that lambda values of this form are eigenvalues, and the corresponding eigenfunctions are these, and that the eigenfunctions are orthogonal. Yay!